Okay, welcome to the second part of lab where we're going to talk about the analysis and the conclusion. This is where we're going to analyze what our data gives us. Let's go on to this next one. We can have some calculations. We can have qualitative calculations. These are where there are no real calculations. You're not using numbers, but you're comparing with a control. So the control was blue, but my experiment showed orange. So I'm comparing back and forth. So I'm analyzing it by comparing. Quantitative, this is where you have to add, subtract, multiply, divide, or do any math function. So that is quantitative calculations or analysis. Now, like on any of the videos, if you need to stop, pause the video, and write down what you need to before you move on, great, do it. I'm going to go on now. When we do analysis, oftentimes it's a lot easier to see the analysis if we do a graph. There are basically three types of graphs that we can use: bar graphs, pie graphs, and line graphs. We don't use pie graphs very much. Pie graphs are a comparison of how much to how much. So I could have put this, what kind of pet, in a pie graph and it still would make sense. But it's really easy to see in a bar graph which one most of the people own as far as a cat versus a dog or goldfish or hamster or rabbit. This is of student grades. It's very easy to see. A lot of them get B's and C's, a few A's and a few D's. It doesn't show the F's. On the bottom here, line graph is what we use a lot in science and especially in labs. So this one right here, we would show the points that we put on and then connect them. We're going to be using Logger Pro, I don't know how many of you are familiar with that, to do a lot of line graphs in chemistry lab. And sometimes we're going to put more than one line on a graph so that we can compare what's going on with those graphs. And we'll be doing that later on in a couple weeks with that. But I'll walk you through the Logger Pro as we get to it. So when we do a graph, the very important things are we need to make sure we label the graph. Now this graph has most things labeled, but it doesn't have a title. You're going to have to come up with a title for your graphs. So as we look at this and we're starting to think, okay, what's on the x-axis, what's on the y-axis? Well, it looks like on the x-axis is years, and I should have probably put that on there, but I didn't. So I should have put years. And on the y-axis, it's global demand for energy in pentawatt hours. So how much energy is needed. So you can sort of see the different things that are graphed. On the orange, we've got global demand, and the yellow is the demand for renewable energy. They're both going up. And you can see in the green that the supply of fossil fuels is going down. So what could we name this graph? We've got to be able to come up with a name for the graph that determines what's being said in this graph. So we could say energy needs of the future, because we're right here at about 2018, right? So we could say energy demands of the future and past, or energy demands, something like that would be good for the graph so you could understand. Notice that they did have a key, and that is very important, especially when you have more than one line. And you will want to color your lines, and I have put out color pencils so that you can do that. All right, so let's go to the next one. We also need to, after we analyze what we've got and we've put it in a graph, we've got to talk about error and source of error. So this is called error analysis. And this is where we bring back into play the precision versus accuracy. How close are you to the actual value? Depending on what the person measures. Is there calculated? You can calculate this formula. I'm not going to be really worried about that. Basically, it's your value minus the accepted value times 100 divided by your value. I call this is percent error. And percent error we'll bringing in later. It's what you got minus what you should have got times 100 divided by what you should have got. So that's the redneck way to remember it. Okay, so precision, remember how fine-tuned are your measurements? How close together are they? How grouped are they? Are they really close, really precise, or are they sort of scattered over a large range? And that depends a lot on the measuring tool that you're using, but it can also be affected by who's taking the measurements. Are they measuring it the same way each time? It's also determined by the number of significant figures. So let's do a practice real quick here. You've got some choices here. We're just going to talk about accurate and precise. So Martin is conducting an experiment. His first test gives him a yield of 5.2 grams. His second test gives him a yield of 1.3 grams. His third test gives him a yield of 8.5 grams. On average, his yield is 5 grams, which is close to the known yield of 5.1 grams of the substance. Which of the following are true? Okay, so look at his results. It's 5.2, 1.3, and 8.5. Are they closely grouped? They're not. So it's not precise. But he has one that's really close. 5.2 is really close to 5.1. So I would say he has something that's accurate. So his results, he does have an accurate one, but they're not precise. They're not all grouped together. Okay, so that would be the best choice, would be A. Let's look at another one. So Jared is practicing for a golf tournament. His normal driver distance is 250 yards. He hit 3 balls with his driver, and they traveled these distances: 190 yards, 195 yards, and 187 yards. Which of the following is true? So what is the accurate? Which one's accurate? What number is accurate? You said 250, you're right. Is he close to 250? No. So his results are not accurate. Okay? So he's not accurate. So anything that says accurate down here we can get rid of. Now we've got to look at precise. Are they closely grouped? And this is where you've got to sort of look at significant figures. So if I go to 2 significant figures, which this is right here, then it's 190. This would round, it depends on what's after that. So it could go 190 or it could go to 200. So 190 would fall in here. This would round up and it would be 190. So they are pretty well grouped according to 2 significant figures. So I would say that they are precise. So the best answer here would be B. His results are precise but not accurate because they're grouped, but they're not what he's been driving. Then we get to conclusion. Now this is where we are going to spend a lot of time in lab. I want you to make sure you do a good conclusion. I don't want it here in your conclusion. This was a fun lab. I want to do it again. That is not a conclusion. That is a statement of what you like. So we're going to do sort of like what they do in English, where you have a claim, you have to show evidence, and you have to justify. Because as a scientist, you have to do that. So what did you learn in lab? What do you know because of lab? Evidence. Use your evidence, which is your data, to tell me how you know that. And then, does that evidence really support your claim? So you've got to finish it up telling me how does that evidence support your claim. And this is the best diagram that I could find that explains this. So your reasoning here is your justification. How does your evidence, so you've given me your claim, you've shown me the evidence, but how does your evidence really support your claim? Okay? So justify it. And we're really going to work on that. So your minimum, you're looking at least 4 to 5 sentences here, with 1 being your claim, 2 to 3 being evidence, and 1 being your justification, tying your claim and your evidence together. Okay? So work hard on that, because that's where a lot of your points in your lab is going to come from. And that's where we're going to stop today. You've got some practice ones to practice, so go ahead and get started on those.